Cool. So the topic of today then, wrapping up futexes, hopefully, and then we'll do a little bit of assembly. Okay, so now I'm not using the HDMI anymore. Now we're on the VGA and still doing the same stuff. We'll do a tiny bit of assembly if we have time. If not, we'll continue that on Friday. So where did we leave off? Right. We were saying we were looking at this implementation of a mutex. So just to very briefly review, we have with our futexes we have a couple of things that we can do. We can call wait on some address, and then your process will just stop until someone calls wake with the same address. So when it says futex here, that's really just an address. And there's one more little trick to that. You give it a value. So now if whatever is stored at that address is this value, then you wait. If it's not, you don't wait. Does anyone remember why?
To do with keys. No, actually I can't explain very well. I know what it does, but I can't explain it.
Anyone else want to take a stab at it? Why do we need this value? Can't we just wait for the futex?
Is it because somebody else might change it?
Yeah. So the problem is, well, it's not really that they could change it. It's someone might call wait before we call wait. So sometimes that doesn't matter, but depending on which operation we're implementing here, it might be very, very important. If you're implementing some condition variables, you don't care, right? Because with a condition variable, when you signal, if no one's there waiting, well, you lost the signal. That's the whole point. But with semaphores, we want to increase the value and decrease the value when they wait, right? So you want to remember that signal. So it's important to know sometimes if someone else has been in there messing between the time that you call wait and the time you actually end up in the wait queue. Okay? There's going to be a bunch of instructions in between, right? There's all this stuff. Whenever you make a system call, and futex is a system call, it's going to have to store all the values of the registers on some little stack for a while, and to probably check your parameters and so on, and then eventually it decides to put you in the wait queue. Then it has checked it, but that's okay. That's sort of beside the point. So now it decides to put you in the wait queue, but maybe it shouldn't actually put you in the wait queue. So we can use this value for that. Very handy little extra parameter, and maybe we'll see why later today.
What decreases the value?
Oh, there's no increase or decrease. The futexes don't care. The only thing here is it'll check if this value is the same as whatever this is pointing at. That's it. And then it's up to us in user space to decide what the value means. So we can leave it at 0, and then it'll always wait. But if we use it as the number for our semaphore, then of course we pass in the value that we thought the semaphore had. We thought it was 0, right? But then it's increased to 1, which means I don't actually have to sleep. Right? So for a semaphore, we want to have the semaphore value in here. For barriers, maybe it's yet a different solution.
Okay, so it's up to us to modify the value that futex points to.
Yes. So this is a pointer, points to some value,
and we're modifying
this
that.
This is the actual value, but you can pass in something else too, right? You can just pass in a 0. It doesn't have to be the value that you thought was in here. You can just say if it is 0, then wait. Right?
So potentially we could have a different use if the value is greater than or less than, right?
Whatever, yeah, if you want, yeah. But the system calls will only check if it's equal.
Right.
And we can do whatever we want on it.
That was the question.
Yeah.
If the value changes, will it wait?
No.
Won't go to sleep, right?
Well, if the value changes before we finish this wait, then we won't go to sleep. But after we go to sleep, if the value changes, nothing happens. So actually, if you think about that a little bit from first principles instead, to sort of try to get the answer to that question without getting it, I'm dictating it. So say I'm just writing to this value. How would anyone know that I'm writing to the value? So we have a bunch of threads. One of them is sleeping, and now Ian's suggestion here is he's not suggesting, he's asking, but say now that we want the thread to wake up whenever someone writes to this value, writes to this address. Is that feasible?
No, we may potentially have like 20 threads looking at one value. So either then we have to think about which thread points there, and then after that value changes, just wake them up.
But how do you even catch that value changing? That's the difficulty here, right? We have some address in memory, and we want to detect that a change is being made to it.
Another thread has to be given.
Yeah. So this wait here, if the thread wasn't put to sleep, then it would work. Because then that core could just spin and keep checking that value and then return whenever the value is changed. So that would work. But now it's asleep. And we're off, I don't know, generating some pretty graphics or something. We're doing something completely different with these cores. So how can we tell that something changed?
We can have some kind of overhead where the value is assigned to check to see if it's one of the values.
Let's see, if the value was what?
You can have overhead so that if the value is changed, to check to see if it's one of those values, but that doesn't seem like a reasonable solution.
One of which values?
A value associated with a few times weight, or
Oh, I see. Yeah, to see if it became different from this. Yeah, okay. But still, you have to detect the fact that this memory address is changed.
But someone changed it, right?
Yeah.
So it'd be up to someone that changed it to notify people.
Yes. So here we are. That other thread that's making a change, it could call wake, and that's how they notify people today. That's how we do it. But say the thread doesn't call wake, and we just want to forget about the wait, right? We want to wait. It just waits until the value changes. Forget about the rest, right? No matter who changes it. What about that?
Periodically wake people up and then make them check the value change.
Yeah, okay. So you did make this kind of wait, you make that sort of a timeout thing, so every second or so you let them check again, and then then you return. Okay. That would kind of work. Of course, it would be very, very slow, because you don't want to check too often, and you don't want to check too seldom. So you have a weird trade-off there. There's a couple of other ways that I could imagine doing it. You could imagine, say, rewriting the code for all the processes that are running, so that every assignment that could potentially be to this pointer, to this value, that it also, say, calls some function and sees if anyone waiting. Maybe calls this. Okay. But that seems extremely inefficient and very, very hard to find all those processes. So let's not do that. There's one more thing you can do. If you're the operating system, and you are here inside Futex Wave, you are the operating system. So now you can change the page tables for all the processes. So you say, for every process, if you try to write to the page that contains this pointer, or contains what this pointer points at, make it read only, the whole whenever anyone tries to write to that page, the OS comes in first. Says, oh, they're trying to write to it. Let me see if they're writing to that exact value, in which case I'll wait the process, and then return and allow the write. So that's one way that you could do it. You could change all the page tables of every process, so that anytime it had to write to that page, which is 4 kilobytes, right? So quite a lot of space. But whenever they try to write to that page, we check. And that's probably the cheapest way to do it, but it's still going to be very expensive.
will it copy the page table? Because the page table is read only and we're operating system, so we can edit something.
The page table is not read-only. The OS always changes it.
So then just say that
Oh, sorry. So for that one page, we flip the bit. So we say, this one is read-only.
yeah.
So now you're going to get a page fault. The OS, whenever someone tries to write to that page, the OS gets a page fault back and says, it checks it, and it just says, okay, that's okay, fine, and then changes it over to read-write and lets them do it. So there's a lot of overhead in it, but it's probably the easiest. Anyway, so I suppose in practice it's not probably a good idea to make it possible to wake up without anyone calling wake, because it's just going to be very expensive to run. Okay, and then there was the count here that says how many do we want to wake up. Okay, so we were looking at this solution here. We had identified 3 potential problems. Let's see if we can remember. So the first one was, whenever we unlock, we call futex wake, no matter what, even if no one's waiting. So that was a little bit wasteful. Want to remember the other 2 problems here?
The value could overflow.
Exactly. So this, I think it's the C here, could go over 4 billion, or actually first over 2 billion, and then around to minus 2 billion, and then up to 0. And whenever it reaches 0 again, then it'll get unlocked, even though it shouldn't. There was one more problem. We call it a live lock.
It was the whole, if they got into the while loop model, things that the while loop kept changing the value and it would keep going back into the while.
Yeah. So here, futex wait checks if the value is C plus 1. So that's good, but then if there are 2 of them running this at the same time, the value might not be C plus 1 when you get in there. In which case you come back, increment it to something else, and the second thread is now checking if it's C plus 2, let's say. And it's no longer because I just incremented it, and so on. So they're both working very hard, but they're actually not going anywhere. And that's called the live lock. The difference between a live lock and a deadlock is in a deadlock, maybe it's not strictly true. In a deadlock, you don't do anything, typically.
Do, right? The word you're saying, live lock.
Live lock.
Oh, live.
Like
Okay.
alive instead of dead. Right? So in a deadlock, you're just sitting there. That's the idea. In a live lock, well, this is not strictly a live lock because there's no locking going on. But either way, you're at least working very hard. So if you have 2 spin locks that are conflicting, you're actually also working very hard, but it's still called deadlock. The definition maybe is a little weak. All right. So anyway, we need a solution to this. So I suppose for C, we want to make sure that this cannot overflow, which we don't solve that by making this an infinite size. Right? We solve it by making sure C doesn't go over some fixed number. And we need a solution for this, and so on. Okay, let's see what's in store here. So I'm again referring to this. Hey, where did I put it? There. This paper. Futexes are tricky, and they are indeed. So if you don't follow everything here, I suggest you read through it. It's a quick and easy read. Well, I wouldn't say easy, but okay, it's a fine read. Let me get a copy of the next solution here. Okay. have three different states that we can be in. C doesn't go between 0 and infinity anymore. It goes, no one has the lock, one person has the lock, or more than one, or not person, more than one thread has the lock. So the idea here is we increment to 1, then we increment to 2, and then whenever another one comes in, we don't increment, right? And we stick with 2. The difficulty becomes, how do we decrement? Because we don't know how many there are. We don't know how many locks anymore, how many lock holders anymore. So we need to kind of try to deal with that. So the initialization is the same here for locking. Compare and exchange, again, it returns the value that used to be there. So now we say, okay, let's see if value is 0. If it is, then make it 1. Right? And then if it wasn't 0, if it was 0, then we're good. We locked it already. Fast and easy. And this actually is a single assembly opcode, so at least it looks short. It takes a while to run because it's an atomic operation. Okay, so if it isn't 0, that means it's either 1 or 2. So someone holds the lock. Okay. So now the problem is we don't know what's happening after. We don't know if someone, it could have been 1, right? But then it became 2 before we got into this next if statement. So we can't actually rely on the C here anymore to say that C is actually going to remain 2. We don't know that that's going to happen. We can just know that whether it's going to remain 1. That is. We don't know it's going to remain 1 if it was 1. So now we have to check it again. So if it was 2, then we're good. We don't have to do the compare and exchange. So in C, it doesn't run whatever is after. So here, this condition is true here, so it has to be true for the whole thing, so it won't execute the rest of the condition. That's a nice little optimization. We didn't have to do it like that, Sarah. Maybe we did. Anyway, so this runs quickly if it's 2. If it's 1, then we say make it 2, right? So there's someone holding it already. Okay, now we need to fake it. So now it's going to be 2. If it was 2 already, we don't need to make any change, right? Because it's already 2. So there's 2 or more holders. And then we wait as long as the value is still 2. Okay, so what could have happened there is the value could have gone down. Right? The value could have gone down while we were doing all this other stuff. Someone left. But if there's 2 of them waiting, then we have to wait. Okay, and then what?
When we're in wait, are we really waiting?
Here?
Yeah.
Yeah, that puts us to sleep if the value is 2. Okay. Okay. And now we have another compare and exchange. What's going on there? Right. So here we're saying if it was 0, make it 1. And now suddenly we're saying if it's 0, make it 2. But it was 0 before, so okay. Let's skip that for a bit and look back at the unlock. So now we're decrementing the value. So if used to be 0, it used to be 1, then we're not doing anything. Then we just bring it down to 0, because no one else is waiting, right? So the decrement, again, that returns the previous value, not the new value after the decrement. So if it was 1, that means no one else is waiting, so whatever, we don't have to wake anyone up. But if it was 2, then it's not 1. And it's clearly not going to be 0, because we're not going to unlock if it's 0. We're holding it, so it has to be 1 or 2. Okay, so this basically means if it's 2, if there was someone else waiting, then we set the value to 0. And then we wake one thread up. Okay, so now it looks like we're saying there's no one waiting, even though there is someone waiting. Very tricky solution.
In Futex is when I wake someone up, can I wake more than one person?
Yes, but specify here
Yeah.
to wake one.
But you know how in conditional variables I could wake
Oh,
someone
it doesn't
up.
happen by accident. No, we just didn't get the one. So,
Let's see if we can draw this.
While loop, right?
So what might happen here is we start with 0, one thread comes in, that's easy. Now the second one comes in, we're at 2, first one decides to release, now we go down to 0. Doesn't seem like an accurate count exactly.
but we wake one up. Right, so now we wake one up. The value is 0. Set it to 2. And then we're done. So now it looks like the value is going to be 2 again. But at least we're done. So that's good.
So what happens next time? Is this what's going to happen here? If it's not 0. Oh! No, the value was... Right, so we go around if it's not... Okay, good. Yeah. So now we're back at 2. Let's see. First thread leaves. First thread leaves. Second thread wakes. Right, so we were here. We were waiting. We got woken up and we set it to 2. And then we're out. I'm missing something. Because now when we unlock,
Ah! Yeah. Okay, so now it's 2. Then when we go and unlock, it's going to go down to 0. It's fine, the count was wrong. But who cares? So
When are we gonna go to online? We were waiting. Someone woke us up.
Oh yeah,
He changed it to 0, but we changed it to 2 on the way
we
up.
changed it to 2 and then we left. And then eventually we're done with our whatever we're doing and we call unlock. That's what you do with locks. You lock and then you unlock. So at some point we unlock. So right now it says it's 2 even though there is only one thread waiting. One thread using it. That seems a little incorrect, but let's see if it matters. So now when we call unlock, this one here triggers. It wasn't 1. We decremented and it went from 2 to 1. It didn't go from 1 to 0. So that means we have to enter here. We set it to 0 and then we wake. There isn't anyone there. So that's wasteful. Right? but it's not incorrect. So it used to be that we just always call futex wait. This time, we only call futex wait if you come in and there's more than one thread, so people are waiting. And then the very last one, when you're actually the only one, but the very last one after that sequence, you also call out futex wait one extra time. So you don't, under the conditions that, it's very common when you're locking stuff that, no one else is waiting. It's very, very common. So under that, in that situation, you go here, and you win right away. You're out. Your unlock doesn't do anything except the atomic decrement. Beautiful. If there is contention, then you start having a little bit extra work. So you have to do the wait, even though there wasn't anything there. And you have a couple of compare. You have to do 3 compare and exchanges in that case. So it gets a little more expensive, but it's certainly well, it has 2 advantages. It doesn't break, right? And it also doesn't run all that slowly. Let's see. So we solved this part. What was the other problem here? Futex wait. Yeah, this part is solved as well. Right? We're not incrementing it over and over. All it's going to increment to is 2. Right? So it used to be it went to 3, even 4 and 5. So every time you go in and check, it's a different value. You try again. But here, you're going around this. All it's going to do is go to 2, and after that, you're settled. So you'll be waiting. Okay, so we are going to do a homework on futexes. Make sure that we understand this right now. So, any questions on this? Why am I bothering you with futexes again? What's wrong with just using a mutex?
Has to do with formats.
Mutexes are implemented using futex. And this is only in Linux too. Of course, if you're going to do this kind of work, you're probably going to either do it in Linux or you'll use a similar mechanism in Windows. So, yeah, the reason we're doing futexes here is that it is the basic primitive for all of the synchronization operations that we use. So we use mutexes, we use barriers, semaphores, condition variables. They're all implemented using futex. Right, so this is the minimal thing that you can implement in your operating system to be able to implement any sort of synchronization operation with a wait queue. The futex is basically just the wait queue, right? You can wait and you can wait. That's it. There's no mutual exclusion in there, really. I don't know why it's called futex, because there's no exclusion, right? But those 4 are not the only synchronization things you necessarily want to do either. So just like we learn assembly, even though most of us are going to use very little assembly in our life, this is one of those low-level things that we don't write. We don't, to be honest, we don't go and implementing our own mallocs very often either. But it's pretty good to know, sort of. Actually, I saw a PhD defense just a couple weeks back, and it implemented this whole complicated tree structure and some sort of mirror stack and stuff because they wanted to keep track of, for every malloc chunk, they need to know how big it is. Right. So they needed it for something else. This was a security talk. So you need to know, whenever you call malloc, it's not just enough to have a memory. You actually need to know how big was that piece. Right? So how do you do that? Well, you have to keep some separate directory and remember for every pointer how big it was, and so on, right? Or
Minus size D.
yeah, maybe you go minus size D and just look what it says over there, because there's the size, right? But if you don't know systems, sometimes you end up wasting your time.
That's
So-
what you did? Seriously?
Yeah.
Would you have known to check minus size T This class?
No, but if I was trying to do a PhD on
Yeah, but this was not a PhD on malloc, huh? This was
I
a
was just kind of deciding.
PhD on security, and nobody does a PhD on malloc. Not these days.
I just mean if I was in that level of detail trying to figure this out.
Yeah, but this was a different.
Process, right? Maybe not.
I don't think so. It's not that. It's not that obvious.
Working with the professor.
You should have just asked too.
Professor didn't know it either. I mean, and I don't blame him. It's just. It's one of those things.
Did you comment?
I commented, yes. That's better believe I commented.
What did
It's
he
like
say? What was his
those
response?
days you spent on this special tree structure, you wasted.
Yeah. Well, I mean, it probably wasn't that complicated, so it wasn't important for the thesis at all. It's just kind of a funny anecdote. You know. No, the work was good, other than that part. Okay, so that's why we're messing with utexes. Let's take one more application here. Actually, we have a. Which one do we do first? Let's do a simple one. So, a barrier. We've done barriers with with semaphores before, and actually that works nicely. But say we don't like to layer all our different sync operations on top of each other and make one big ball of spaghetti. We just want to use the basic primitives. So what might a barrier look like? Happens to be some more sample code, so I'll gladly copy paste. It's the start of it. See. All right, so this barrier implementation, it keeps track of what your the n here is the initial needed, like how many we're supposed to have, and then there's the still needed, which is how far we're from the difference. So it starts out at initial needed and it decrements until you reach 0. Right? So it's almost the same as incrementing until you reach the n. So we have a regular lock around it, and then we say decrement are still needed because we got one more thread coming in, and if it happens to be equal, let's see. Okay, so this event here, this is just to, it keeps incrementing. This is just to see, did anyone else come in and change this while we were working on it? So that is not related to the barrier count. So now if we need more than one still, then we unlock and we wait. Right? And we get woken up. So you could get woken up. This is signal handling, I think. You get woken up for some other reason. Now, if it happens to be the same, we go back to wait. Okay, that's fine. So now we're waiting until, okay. What am I missing here? Oh, yeah. Okay. So the event only goes up when everyone's there. Right? So you wait for this event value to change. And when suddenly still needed is 0, then we increment it. So now, next time we evaluate this, it'll be false. So we can exit. And then we wake everyone. So pretty basic barrier. All right, so almost everyone goes in here, and they wait for event to change. All right. This wouldn't necessarily have to be a do-while loop. This is for the signals. So it could be just a wait. And then event change. When the last one comes in at 0, event changes. And then we restart this at initial needed. And then we wake everyone up. Let's see, do we have the same problem here? Is this a reusable barrier? I'm not sure.
But you do still needed is equal to initial needed.
Hmm?
You do still needed is equal to initial needed.
Yeah.
Certainly suggest that it's trying to be reusable.
Oh, never mind. But
We used to have this problem before. We set it to 0, right? And then
We woke everyone up. That's not.
So what was the problem in the previous one? Ah!
in the previous one, everyone was decrementing the value by 1 as they leave the barrier, right? So we're doing this with semaphores. So here we have the luxury, perhaps, of doing a direct assignment. And we also have the luxury of waking everyone up right away. So you don't get to do a post and then another post and another post and wake people up in slowly. You can take all of them in one fell swoop. Yeah, so this looks like it is a reusable barrier, and it's actually much easier than the semaphore implementation. Imagine that. Now we're using low-level APIs, and we do something much easier than trying with semaphores. Same thing with, yep.
What is that? Just C++ thing. What is that? That's called the constructor list. Right? Why is mutex empty right there? Right after barrier.
Ah.
What is that?
Probably just initializes null.
It's supposed to be a lot. Yeah. What is it even? I don't even know mutex. Where that comes from.
Yeah, that's a typo. I think it should be this one here.
I was like, I don't understand.
I don't know why. I mean, that seems really strange. It ought to be initialized to something.
Yeah.
Maybe by default it's null.
I think he's using his previous declaration of mutex that we just did. Because he defined what mutex was in the previous page.
No, that's all there is.
Yeah, but I'm saying, so he's also, when he wrote the mutex, he's using his mutex implementation for the lock.
Oh, sure, yeah.
So
But-
when he
but what is
initializes it, it initializes to 0 in the implementation anyway.
Oh, okay. Right, okay.
Oh,
But
so
still,
it's
why have this in the line here? That's, maybe it's calling the constructor.
Or just specifically, maybe it's not assigning anything to it.
Yeah.
Maybe it's like, okay, this is a constructor. I have to assign, have it in my initialization list.
Yeah.
But I don't want it actually initialized, so just leave it empty.
I think that's what it is. These are all, if these are variables, I'm not good enough at C++.
Okay, that's an initialization list.
These are variables with straight initialization. But here it's probably calling the constructor.
Oh,
The construction
I see.
initializes.
Right.
Yeah.
Probably that's what it is. C++ is an incredibly complicated language. And it doesn't get better when you start talking about concurrency, because there's the memory models. Maybe we'll talk about that on Friday. Now it's well defined actually what happens when you have multiple threads accessing a single variable, but it used to not be. It used to be you couldn't really tell which order you would get values and stuff, but I think it's well defined now from 2011.
In Futex wake, we could just say event and then initial needed, and not event and then int max, right?
Let's see. Here? Oh, here. Wake, yeah. Yes. That should work just fine. Yeah. Could you go with initial needed instead? I don't think it would make any difference. But, I mean, positive or negative. Okay. So, we've done the barrier. That one was pretty easy.
Now, you remember how I eventually gave up on making condition variables with semaphores?
There's a whole research paper on how you can do it. And I don't know why. See if I can, here. So I guess a reason why you might want to do it is condition variables aren't available everywhere, but semaphores are more or less available on every operating system. But actually, it wasn't that much of a research paper. It's probably more of a tech report. But anyway, so these are broken implementations here. This is how you have to do it. lots of different semaphores, and it was pretty tricky. So, and then it turned out it was really, really slow. So their conclusion in the end of the paper is, well, that was interesting. We just did it with some low-level API instead, and it was really easy. So let's see what goes on in a condition variable. There, it's basically the same thing, but we have a couple of tricky bits with a condition variable, right? So you can have a wait, and you can have a signal, and then you can have a broadcast. So there was one interesting point there.
We can imagine how to do these things, right? So it's pretty straightforward. Mutex wait. Signal, pretty straightforward. Mutex wait, right? Wait 1 exactly. So that's pretty straightforward. What about broadcast?
Wait, maxint.
Wait maxint. Okay, we're good.
Assuming
So-
that you only have maxint things. Wait.
That's a fair assumption. Let's not have 4 billion threads waiting. Yeah. So, but there's an interesting performance challenge here.
If you recall, the wait actually takes a variable and a mutex. And then the others take vars. And the idea here is you have to hold the mutex when you call wait, and then you release it, and then when you wake up, you hold the mutex again. So now, when you call broadcast, what's going to happen? Now we wake up all the threads. We have not 4 billion, but maybe we have 100 threads. We wake them all up. They all try to get this mutex. How many get it? 1. Right? So now we have all this work, all these threads spinning up. Maybe you have 100 cores. They're taking over all these 100 cores. They're all trying to access this one variable, the mutex, to try to increase it or decrease it. And then you realize, oh, it's 1. Okay, go back to sleep. A lot of work there. So there's 2 things that are a lot of work. One is the fact that they have to wake up and go to sleep, and there's quite a bit there. The other one is all these cores are accessing the same variable. So this is it's called cache contention. So what happens if you have two CPU cores? They try to write to the same place in memory. Or one tries to read and the other one tries to write. As long as they don't both read, there's a problem. So now if I write to the first byte, and you write to the last byte, what's going to happen? I write to my cache, my first byte is changed. You write to your cache, your last byte is changed. And now you flush that out to main memory in chunks of 64 bytes. That's just how things work. Right? You write out these cache lines in and out. So one of our writes is going to get lost, right? I wrote to the first, you wrote to the last, only one of these cache lines make it. That's actually not good, right? So it doesn't work that way. Writes don't get lost. But in order to avoid writes getting lost, they have to check with each other. So now, all these CPUs, when they try to write to a cache line, they have to check with the other CPUs that they're not writing to the same one. In fact, I'm not 100% sure here, but I think they only keep a cache line. Either I get to cache a certain line, or you get to cache a certain line. We don't all cache the same line because of this problem. Yeah.
Is it for every instruction? The whole course have to check, hey, are you reading this?
Well, so I think in order to avoid that, what they do is they make sure whenever you fetch a cache line, you make sure you're the only one. Some architectures might be able. It's sort of like that exclusive read that we saw in ARM. So some architectures might support where you say, oh, I can have a shared read. So as long as there aren't any writers, we'll all have the cache line. But anyway, anytime I want to try to write to a cache line, I have to tell the other cores that may have it to get rid of it. If they are writing to it at the moment, I have to wait until they're done writing, and then I have to get it, copy it over to my CPU. I make some changes, and they want to write it, copy it over to there, they make some changes, right? So now you imagine you have these 100 CPUs, all on one die, right? Nicely integrated. So now they're all fighting for this one. They're copying these 64 bytes back and forth and back and forth and back and forth and going to sleep. That's actually what would happen if we were to implement a conditional variable this way.
So then, what? While loop of Vutex wait count 1 for X amount of times?
Doesn't help.
No, I didn't think so.
Because now you're waking one, waking another, and you're very quickly going to wake all of them, and they're still going to be sort of fighting about it.
But are they trying to see if the value is what they think it is? Like, are they trying to read?
No, they're trying to get a lock. It's a compare and swap. Right? So they have to write to it if it's yeah.
Okay.
So there's there's a huge fight now for this one cache line, using a very precious resource, the communication lines between the CPUs. So it's going to slow everything down. Even if you have some other programs running on some other cores, probably it's all going to slow down because these guys are fighting. So in order to solve that, there's one extra call in the Vutex API that I haven't mentioned. And let me just try to write it out right, and then we'll leave. It's called Vutex requeue. So there you specify again the Vutex, wake up count, and then a oh, I lost my train of thought. Wake up count, and then another queue, and then we have a requeue count. So what happens here is you say, okay, I'll wake up just one, and then we take all the other ones away from here, put it in a different queue. And this, in our case, would be a queue for the mutex. Right, so our mutex already is going to have a queue. And that's just how we implement mutexes. So here we just say, okay, one of you gets to wake up, everyone else, here's a mutex queue, go sit in that. And next time I've woken up and I say unlock, well, what I'm anyway going to do is wake up whoever's waiting for this mutex, so it'll just work. So this is sort of an optimization. You don't need it. You can always do it other ways, but it's much, much faster because now you have one core waking up and another core shuffling things over, right, from one queue to another queue, and all the other threads are just the same. Okay, I think that's probably enough Vutexes. So next time we'll do a little bit of assembly and maybe some performance measurements and that sort of thing. Only a tiny, tiny bit of assembly, don't worry. All right, so I'll see you on Friday.